Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we're going to be looking at our third set of notes. Now, yesterday we talked about the 5 different types of reactions. Today we're going to learn to use clues to figure out which reaction type really is occurring, and then apply that trend to actually predict what products is. So what we're really doing today is real chemistry. You're going to look at what's going on, and you're going to figure out what you make, and you're going to balance it. Now, in order to do that, we're going to be making new compounds and new elements. So the stuff on the product side today, we're not going to know what it is. That's our job to figure it out. So I'm going to remind you of this at the beginning and at the end here because it's that important. So don't forget, whenever we're making a new product formula, we have to ask ourselves, is it an elemental substance or a compound that we're making? Now, if it's an elemental substance, to get the right formula, and without the right formula, you're not going to get the right balanced equation, you have to remember, is it diatomic? Is it Han-Fickel-Bry? So whenever we make an element, like in single replacement, element in a compound makes an element in a compound. We're making an element. Decomposition, the type of decomposition we're going to look at is where we break apart into 2 elements. That's the simplest one that's easy to predict. So we always need to ask ourselves, is that element Han-Fickel-Bry? If it is, we have to put a subscript 2, or else it's just not going to balance right, and it's not going to end up reflecting what actually happens in the real world. And then second, you're going to make compounds. And quite often you're going to make compounds. Now, some of them are simple, like in in combustion reaction, when it's hydrocarbon combustion, we make CO2 and H2O. We know those are 2 new compounds, but we make carbon dioxide and water. We know their formulas, we write them down. But in every other case, we're actually putting together and making an ionic compound. So we got to remember to get its correct formula and therefore get the right balanced equation and therefore correctly reflect what happens in the real world, we need to check charges and then crisscross reduce. And remember, that means back of the periodic table. So you look up the formulas and charges on the back and then crisscross reduce to find the smallest number of cations and anions that gives us a neutral compound. So remember, check charges, write them, crisscross reduce, and then you've got your correct product formula. If you don't remember to do these things, all of the stuff you do will be wrong. So this is really, really core ideas that get applied in almost every reaction type situation where we're predicting what happens. So we're still looking at the same section of the chapter, but now instead of just saying, oh, that's combustion, that's single replacement, that's double replacement, we're actually going to do the single and double replacement and so forth. So we're going to do real chemistry. Now, if you recall yesterday, I said in synthesis or combination reactions, we got 2 or more substances combining to make a single product. Now, there's simple elemental combination, and then there's more complex combining. You don't know enough chemistry, and I don't expect you to learn it this year to be able to handle the harder stuff. So what you're actually doing, sorry, I just stepped on the cord and just about knocked off the headset. What you're actually doing in this problem is too hard for you to physically do. Now, you could learn that metal oxides in water make metal hydroxides, but that's beyond the chemistry we're looking at. So we're not going to ask you to do this type of synthesis or combination. The type of synthesis or combination you need to be able to handle is when we have 2 elements. So here's the key. 2 elements. It's like 2 Lego blocks. All you can do with them is stick them together and make a compound. So elemental synthesis or elemental combination is the type you need to know for this homework stuff. So when we're predicting products, you need to know just elemental combination. And basically, we're taking the 2 elements and we're putting them together to make a compound. So here's where we go back to what we looked at in the last slide. When you're combining to make a single compound, all you're really doing is looking up the charges. Mg is a 2 plus in the back of the table. Oxygen, because it's not O2. That's O2 because it's Han-Fickel-Bry and it's an element. But when it's in a compound, it's oxygen atoms, and that's O2 minus in this case. So Mg2 plus O2 minus, well, and I'm going to do it off the side because remember, when we write our final formulas of our products, we don't want to include these charges there. So if I have magnesium and oxygen combining, the back of the periodic table tells me Mg2 plus O2 minus. I crisscross reduce. So that 2 goes down there, that 2 goes down there, and 2 to 2 reduces to 1 to 1. That's my answer. Magnesium oxide is what I'm making, and it's going to have a formula of MgO. So first, decide what it is. Synthesis, that means make one product. and then correctly predict that product's formula, MgO. Now we're ready to balance. And this is why we have to balance, is because these are the correct formulas and it's not balanced at this point. So it can't be happening this way in the real world. So since we started with two O's, we got to end up with two O's, which means two magnesium oxides, and that means we needed to start with two magnesiums. So this would be the correct balanced equation for the synthesis reaction between magnesium and oxygen to make magnesium oxide. Two magnesiums, one oxygen molecule makes two formula units of magnesium oxide. Now, the next one we're going to look at is decomposition, kind of the same thing in reverse. So remember, one reactant, dead giveaway. So this one's easier to see. If I see one reactant, gotta be decomposing. Now, just like the last one, there's simple and there's more complex. I don't expect you to know enough chemistry to be able to predict how a compound breaks into multiple compounds. But if you had a simple binary two-element compound, I would expect you to understand, oh, all I can do with that is break it into its elements. So silver oxide, Ag2O, is going to break apart into silver and oxygen. Now I'm making elements, so here's what I got to ask myself, Han-Fickelbrei. Is silver Han-Fickelbrei? No. So I write Ag. Is oxygen Han-Fickelbrei? Yes, it is. So I have to have O2. And if I forget to do that, it's going to be wrong, because now I balance it. I need to start with two oxygens if I'm going to end up with two oxygens. So I know I've got to have a 2 there, and that means I need 4 silvers over here being produced. So it's a 2-4-1 balanced equation. And that's exactly how this happens. You get 4 times as many silver atoms as you get oxygen molecules being produced. So that would be decomposition. Once again, we only look at elemental forms of this type of reaction. So elemental synthesis, elemental decomposition, should be able to handle those. That brings us to our hydrocarbon combustion. And remember, hydrocarbon combustion is the one we're really going to isolate here. We talked about elemental combustion, but that's really just synthesis. And what we talked about a second ago would remind us of how to do that type of thing. So what we want to key in on is the hydrocarbon combustion type. Now, if you see you've got a hydrocarbon, C3H8, carbon and hydrogen, or C's, H's, and O's, an oxygenated hydrocarbon, it's going to be hydrocarbon combustion. Now, in this particular case, the problem would say something like, when you combust C3H8, what is the balanced chemical equation? So the combusting part is reminding me, oh, okay, I'm reacting with oxygen. So I know my other reactant here is oxygen. To burn anything, you need oxygen to support the combustion. And the nice thing about hydrocarbon combustion, we don't need to worry about what are our product formulas. They're always the same thing. You always get CO2 and H2O. Now, this is one of the types of problems that's sometimes trickier to balance. Sometimes get in trouble and have to double. But now I've got the right formulas. Now I can worry about balancing it. I've got 3 carbons, so make 3 CO2s. I've got 8 hydrogens in my C3H8. And C3H8 is actually propane. So if you have a propane camp stove, then you're burning C3H8. So 8 hydrogens on the left, that means I need the 4 waters on the right to get 8 hydrogens on the right. And then to finish it, I have 3 CO2s, that gives me 6 oxygens. Oops, cutting off at the bottom there. So right up top, that would be 6 oxygens. And 4 waters, that would give me 4 more oxygens. 6 plus 4 is 10. I need 5 O2s to make this balanced equation work. So 1 C3H8 reacts with 5 oxygens and makes 3 CO2s and 4 H2Os. So hydrocarbon combustion, always the same thing. Other reactant is oxygen, always make CO2 and H2O. From that respect, once you know what you're doing, it's actually one of the easier type, because you don't need to predict anything. It's always going to be the same. Now, next one, single replacement. Got to spend some time with this, because single replacement is the one that might not happen, and we got to learn how to use an activity series to see if it does. But remember, it comes in one of 2 forms: a metal attempting to replace the metal in a compound, or a non-metal attempting to replace the non-metal in the compound. And while it is possible we could have the bottom type, we pretty much exclusively look at metals attempting to replace in a single replacement. So we don't really worry about the non-metal one. In fact, on page 361, it's an activity series of metals. So it's a list from top to bottom of most reactive to least reactive metals. So the first type is the one we're really going to key more on here. You should understand the second, but the first one is the one we always do in practice. So here's an example of an incomplete activity series. This is just a simple list. And the way it's written is lithium's on top, zinc's on the bottom. So that must mean lithium is more reactive than potassium, which is more reactive than calcium, and on down the line. Now the reason that's important is a single replacement reaction will only occur if the elemental substance is more reactive than the metal that's in the compound, and then it'll take its place. A reaction occurs, and it's more chemically reactive then. So when we do a single replacement, we have to think this through. So if we look at the reaction Li and NaOH, Li is higher, which if you look, that means because the activity series is highest to lowest in reactivity, Li is higher or more reactive than sodium, so it is chemically reactive enough to kick it out of the compound and take its place. So sodium gets left out in the cold and is now an elemental substance, and lithium has now taken the place of the sodium in solution. So this is an example of a single replacement reaction that actually occurs. And that's because the lithium was higher than the sodium. So basically, is the element more reactive than the like element? That's what you're asking yourself. So always look at it from the viewpoint of the element that's attempting to replace. Now, if we look at this situation, zinc is actually lower or less reactive than aluminum, and therefore it's not reactive enough to take its place in the compound. So aluminum chloride is going to stay together, and the zinc is not going to do anything. It's not strong enough to force the aluminum out of solution and take its place. So zinc metal, when you would throw it in aqueous aluminum chloride, doesn't cause any reaction at all. And that's because the zinc is not strong enough to force out the aluminum and cause the reaction to occur. So aluminum's more reactive. It gets the compound. It already has it, so nothing's going to occur. So let's try a couple here. In the first one, I got magnesium with lithium nitrate. Second one, I've got sodium with zinc nitrate. Now remember, first you need to ask yourself, what's the metal in the compound? Okay, that's lithium. It's always the first one. That's where we put the metal in an ionic compound. So we're asking ourselves, is magnesium strong enough to kick out lithium? Well, magnesium is below lithium. So no, it is not strong enough to kick out the lithium. And we're going to put no reaction. Now, if you wanted, you could put Mg plus LiNO3 because that's true. You're going to end up with the same thing you started with, but it's easier just to put Nr, no reaction. Now in the second one, sodium is attempting to replace something. Remember, as a metal, it's going to attempt to replace the metal. That would be the zinc. Well, sodium is higher than zinc. So yes, sodium is reactive enough to kick out the zinc and take its place. Now, here's where you got to go back to what we started this whole set of notes with. When we make elements, you talk about Hahn-Fickelbrei, is it diatomic? When you make compounds, you crisscross reduce because it's an ionic thing we're typically looking at. Here I'm making both because when sodium kicks out zinc, zinc is now alone. So you have to ask yourself, is zinc Hahn-Fickelbrei? And the answer is no, it's not. So Zn just is plain Zn. That's one of our reactants. Now, sodium ends up with nitrate, and here's where we're making a compound. You got to be careful. At this point, most of my students will say, okay, I've got AN with NO3. That's my formula, Mr. Brown. Well, the problem is that's not a valid formula. Remember, we're making an ionic compound. Ionic compounds have to be neutral. So when you look up sodium, you will see Na+. When you look up NO32, you won't find NO32. You'll find NO3 nitrate, and it's a -1. So when I crisscross a +1, -1, I get one of each. That's my proper formula. And if I don't get the right formula, I can't get the right balanced equation, and I won't be accurately describing what's happening in the real world. So every time you make an element, Hahn-Fickelbrei. Every time you make a compound, crisscross reduce. And remember, you don't need to memorize them. Look it up at the back of the periodic table. You always have access to that. And then crisscross reduce your charge values. And then finally, now because I've changed, I've got to check to see if I'm still balanced. Well, I'm not. I started with 2 nitrates, 2 NO3s, and I ended up with only 1 in sodium nitrate. So I need to put a 2 there, which means I needed to start with 2 sodiums. So this is a 2-1-1-2 balanced equation. Single replacement, got a number of things going on here. It's one of the trickier ones. So remember, an element in a compound and the element's not oxygen, we're attempting to do single replacement, so we need an activity series. So when you're doing your assignment from your homework, look in the activity series in your notes, and if it's not there, you gotta go to page, I believe it's 361. It's mentioned earlier in the notes to actually see where the things are to see if it happens or not. Okay, last one we're going to look at is double replacement. And since we got 2 replacements, that's going to be harder. We got more going on. But no, it's actually a little bit easier because all the double replacements we look at, we're actually going to double replace. So we don't have to decide if a reaction occurs or not. So remember what we talked about earlier is in a double replacement, A and B are trading places. In other words, our cation swap. You could also look at it as X and Y are trading places, same difference. But it's easier to find the first thing in the compound because it's the first thing listed and swap those two things. So in this case, we got two compounds on the left, and you'll notice the sodium and the cadmium traded places. Now, you don't have the same subscripts on each side. We had two nitrates on the left and only one NO3 on the right. And we had two sodiums on the left and we only had one on the right. And that's why we have to balance it. So remember, we're making two compounds. We twice have to look up charges, crisscross reduce. So if we're looking at two compounds reacting, you've got to do the crisscross reduce twice. So first I identify what my starting substances are. Oops, black won't write in the way that's visible, so let's go to red. So those are my first substances on each side, so that's what I'm going to swap. So I know calcium Ca is now going to be with Cl. Now, I'm not worried about formula yet, I'm just looking at what's going to be together. And I know hydrogen is going to be with hydroxide, which is OH. But once again, I'm not worrying what the formula is yet. I'm going to figure that out in a second. But that's what I know is going to happen is the calcium was with the hydroxide. Now the hydrogen is going to be with the hydroxide. And the calcium is going to be with the chlorine. So finding formulas. Look up on the back. Calcium is a Ca2 plus. Chloride is a -1. And if this said Cl2 right here, it doesn't. But if it did, you would notice on the back, oh, it only says Cl minus. So I wouldn't put Cl2 down. I just put Cl minus. Now I crisscross reduce. Crisscross 1 and 2. That's my formula. I make calcium chloride, which is CaCl2. Then I do the same thing with the H and the OH. When I look it up on the back, that's a +1, that's a -1, that's a 1-to-1. So I get HOH. Well, another way to write this is H2O. Means the same thing, but it's not wrong to write it as HOH. So that's how I'm going to leave it. Now, because I haven't worried about balancing yet, that's the last thing I need to look at. So based upon those are the formulas that have to exist, what would my balanced equation be? Well, I ended with 2 chlorides, so I got to start with 2. I started with 2 OHs, I got to end with 2. And that gives me 2 hydrogens, 1 Ca, 1 Ca. Looks like everything's good. So it's a 1-2, 1-2 balanced equation. So double replacement, it's not as much going on as single replacement, but it does take a bit of work because we have to do 2 crisscross reduces to get our correct formulas before we worry about balancing. And remember, we always balance last. Don't try and balance ahead of time or you'll constantly get it wrong. When you have elements, it's always about, is it diatomic and Hahn-Figel-Bry? And when you have compounds, for the ones we're looking at, it's always going to be about find the formula of ionic compound, which means check your charges on the back, crisscross reduce, and you will have your compounds formula. So that ends our third set of notes.